In this lesson, we will talk about descriptive analytics for univariate quantitative data. So descriptive analytics for univariate quantitative data. Say we have a single column of ungrouped quantitative data like this. Because there is one column of data, order amount. The other column here is just order ID, which is an ID field, so it's not really data. So we have univariate data and it's ungrouped. We're going to look at two examples. Both are univariate, both are ungrouped, and both are quantitative. And in this example, they are also both continuous. So we have these two examples of ungrouped quantitative data. Now each of these columns is telling a different story. Just visually, if we examine the two columns of data, we can say that most of the values in the first column are smaller than in the second column. We can also say that there's a high variability of values in the first column compared to the second column. Now, these are very small examples, only 25 rows of data, and we can say a few things by just a visual examination. But when we have millions and billions of rows of data, we can't even see the entire data at once. So we cannot really make any meaningful observations. We need a more formal approach. So in this lesson, we will learn how to make sense of univariate quantitative data systematically. We will first look at ungrouped data, then later we will learn how to group it, and then what to do with grouped data. And in this example, order amount is continuous in nature, but later we will look at examples of discrete quantitative variables as well. But most of the descriptive analytics is common to both continuous and discrete. So even though in this example we have continuous data, we will also be learning about descriptive analytics for discrete data because there are some common things to both. But later we will look at examples of discrete data and see the differences. So how do we systematically tell the story behind a column of ungrouped quantitative data? We compute what are called some summary measures, both for discrete and continuous. Measures of central tendency, measures of variation, measures of location, and measures of shape. We will look at these in more detail in the next few slides. In addition to summary measures, we draw some charts. Now for ungrouped data, for continuous, not for discrete, we create what is called a box and whisker chart. That's all we can do with ungrouped data. To do more descriptive analytics, we convert the ungrouped data into grouped data. We convert it to grouped data, and then we create a frequency distribution table. We draw a histogram, we draw a frequency polygon, and we draw an ogive. Now, these four things we do only if the original data was continuous, not if it was discrete. If it was discrete, we would still convert it to group data and create a frequency distribution table and column chart or bar chart of frequencies. We will not do histogram, frequency polygon, and ogive here. And there's a difference between this frequency distribution table and this frequency distribution table. This is for continuous. So the frequencies here are for ranges of values. The frequencies here are for each unique discrete value. So that's the difference. Now note that sometimes if a discrete variable happens to have lots of unique values, like hundreds and thousands of millions of unique values, then this variable may be treated as continuous, and the descriptive analytics that was applicable to continuous can be applied to discrete. But usually in practice, when we have discrete variables, there's not that many distinct or unique discrete values, in which case we do not do these things, instead we do these things. Later, with some examples, this will become more clear. Next, we will study these summary measures in more detail. Summary measures for quantitative discrete and continuous. Measures of central tendency, measures of variation or spread or dispersion, measures of location, and measures of shape. Next, we will look at measures of central tendency. There are three measures of central tendency. The mean, which is nothing but the average value. The median, which is nothing but the middle value. You sort all the values from lowest to highest and find the middle value. Mode is the most frequently occurring value. So what you do is, for each unique value, you find how many times that value appears. That means you compute the frequency of each unique value and then find the value that has the highest frequency. Measures of variation, spread or dispersion. Variance. Variance is average squared deviations from the mean. Standard deviation is nothing but the square root of variance. Mean absolute deviation is the average absolute deviation from the mean. Range is nothing but maximum value minus the minimum value. Interquartile range is third quartile minus the first quartile. Next, we will look at measures of location. Measures of location. Max, which is the same as highest value. Min, same as lowest value. Quartiles, first quartile, second quartile, third quartile, and fourth quartile. Fourth quartile is nothing but the highest value. So you sort all the values from lowest to highest, and the middle value is called the second quartile. And in the lower half of all the values, you find the middle, and that's the first quartile. So below the first quartile, a quarter of all the values lie. Below the second quartile, half of all the values lie. Now, so first quartile is basically 25th percentile. The second quartile is basically 50th percentile. The third quartile is basically 75th percentile. But if I wanted, let's say, 60th percentile, then I can compute 60th percentile. I can arrange all the values from lowest to highest and find the value below which 60% of the values lie, and that would be the 60th percentile. Measures of shape. Skewness. Skewness is a measure of asymmetry of the distribution. So the question is, shape of what? Shape of the distribution of values. An example will make it clear. So this is the distribution of the values. So what does it mean by a distribution of values? So these are the values, 1 through 7. The value of 2 appears about 12 times. The value of 1 appears 4 times. The value of 3 appears about 7 times. The value of 6 appears once. The value of 7 appears once. So the high values have low frequencies. Low values have high frequencies. So that's how these values are distributed. That's the distribution. In this example, the distribution is not symmetric around the middle value. The distribution is more focused around the lower values. That means it's skewed to the right. So it has a positive skewness value. In this example, this is symmetric distribution. So there's a high frequency of middle values, low frequencies of low values, low frequencies of high values. So skewness is 0. Here the skewness is negative because there's a high frequency of high values and low frequencies of low values. So the distribution is skewed to the left. So this is also called the tail of the distribution. This is the peak of the distribution. So if the distribution is skewed to the right, we have a thin right tail. If the distribution is skewed to the left, we have a thin left tail. If there is no skewness, we have equally distributed tails on both sides. Another measure of shape is kurtosis. It's a measure of peakedness of the distribution. An example will make it clear. There's a high peak and a narrow peak. That's a high kurtosis number. Here the peak is not that high. It is not that well defined. The kurtosis value is smaller. Now here, because the peak is high and narrow, the tails are thinner. Here the tails are not as thin as here. Here the tails are even thicker because the kurtosis is actually negative here. So there's not as much of a peak here as here or here, and the tails are much thicker here compared to here, which are much thinner. Here they're even thinner. So even without looking at these shapes, just by the values of skewness and kurtosis, we can tell the shape. Okay, now that we have understood all these measures, let's now look at the formulas and functions for these measures. Formulas and Excel functions for descriptive analytics. So what are the formulas and functions for the measures of central tendency? Remember, there were three measures of central tendency: mean, median, and mode. Mean is sum of all the values divided by the number of values. In Excel, there's a function called average. Array just is the range of values. There is no function called mean. The function is called average. Median, there is really no formula. Instead, there's a procedure. The procedure is you sort the data from lowest to highest and find the middle value. If there are two middle values, you take the average of the two middle values. In Excel, we can use the function median. So in Excel, when we use this function, Excel performs a procedure to find the middle value, but we don't have to know how it does it. Mode, again, there is no formula. Instead, there's a procedure. You find the frequency of each possible unique value, and the value that has the highest frequency, that's your mode. In Excel, there's a function called mode. When you use this function, Excel carries out that procedure for you, but we don't have to know how Excel does that. Formulas and functions for measures of variation. Range, find the highest value, which is a procedure, minus lowest value, which is a procedure. In Excel, we can use the function max minus min. Now, there is no range function in Excel. There's a concept of range in Excel, which is a completely different thing. That's a range of cells. Here we are talking about range of values from highest to lowest. Variance and standard deviation. Now, variance and standard deviation are of two types: population variance and sample variance. The difference is very minor. For most practical purposes, this difference is quite meaningless. The difference is only meaningful for some theoretical purposes, and we will not get into those theoretical purposes. But as analytics professionals, we should just know that there are two types of variances and two types of standard deviations. Population variance, you find the sum of the squared deviations from the mean and divide by the total number of values, so you get the average squared deviations from the mean. Excel functions, where p or where dot p. Sample variance, instead of dividing by n, we divide by n minus 1. That's the only difference. Excel functions, we don't use the p, we use s instead. Instead of dot p, dot s. And if we do not use either s or p, just where, it gives you sample variance. Now, standard deviation is nothing but the square root of variance. So this is the population variance, the square root of that is population standard deviation. There's the sample variance, so the square root of that is sample standard deviation. Excel, stdevp or stdev dot p, or square root of where dot p or square root of where p. Here stdev without the p or the s will give us the sample standard deviation. Or we can put a dot s, or we can put an s, or we can just do square root of the where. Mean absolute deviation is the average of the absolute deviations from the mean. There is no Excel function for mean absolute deviation, and that's because nobody really uses this metric. Everybody just uses variance or standard deviation. Standard deviation is the most popular measure of variance. Interquartile range is third quartile minus the first quartile. We've talked about these quartiles briefly. In the next sheet, we will look at the functions. The Excel functions, there's a quartile function for the third quartile, and there's a function for the first quartile. Formulas and functions for measures of location. Highest value, there is no formula, there's a procedure, but there's an Excel function called max. Lowest value, no formula, but a procedure. Excel has a function. First quartile, second quartile, third quartile, it's all a procedure, but Excel has functions: quartile 1, quartile 2, quartile 3. Percentile has a function in Excel, percentile array comma x. So if I want to find 60th percentile, my x will be 0.6. Next, we'll look at measures of shape, formulas and functions. Skewness. So there is actually a very complex formula, and it is so complex that I don't even want to write it here. Similarly, kurtosis, very complex formula. Even as analytics professional, you really don't have to memorize that formula or know anything about it. As long as you know how to compute it in Excel, you're good to go. In Excel, you can compute skewness using the skew function and kurtosis using the kurt function. Okay, so that completes our discussion of the formulas and functions for all of the summary measures. So now let's apply these measures on our example data. So here's our first example, here's our second example, and here for both these examples we have computed the three measures of central tendency: mean, median, mode, mean, median, mode. We have computed several measures of variance, standard deviation, range, and interquartile range. We did not show population variance and sample variance separately here to save some space. Measures of location: min, max, Q1, Q2, Q3, Q4, and percentile. Well, here we picked 60th percentile. And kurtosis and skewness. So just by looking at these summary measures and without looking at this at all, as an analytics professional, you should be able to tell a story about this data. Now, here this data has only 25 rows of record, but you could have these summary measures for millions of rows of data. So here we have 25. I could have had millions, billions, but only so many summary measures. And just by looking at this, I can tell a story. So by looking at these values, these measures, we can tell story of each column. We can even compare the stories of the two columns. So we can make some observations such as, see, this average here is quite a bit less than this average here, less than 1/3 or almost 1/3 of this. If you look at the standard deviation, it's quite a bit higher than this. So there's more variability in the data here than here. We can say that by looking at these two values. Also notice that the median here is quite a bit less than the mean here. In other words, the mean here is quite a bit higher than the median here. And that tells us that there are some high values which are pulling the mean higher. Whereas here, it's the opposite. The mean is lower than the median, which means there are some low values here that are pulling the mean lower. If you look at the skewness values, 1.25 and 0.2, so this tells us that this distribution is a lot more skewed to the right than this. In fact, this value is so close to 0 that this is hardly much of a skewness to the right, but slightly skewed to the right. So we can make these observations without looking at the original data, just by looking at these numbers. Note that we can also obtain many of these measures using the data analysis pack add-in in Excel, and there'll be a separate video about that. Okay, so we're done with the summary measures. What about the charts? Now remember, for ungrouped continuous quantitative variable, we can draw a box and whisker chart. So what's a box and whisker chart? There's a box and there's a whisker, two whiskers, one on each side. So at the boundaries of these whiskers and this box, we have some critical values. The lowest value appears at the edge of this whisker. The highest value appears at the edge of this whisker. The first quartile appears at the lower edge of this box, and the third quartile appears at the upper edge of this box. And then we draw a line within this box that represents a median or the second quartile, same thing. And then we show the mean either with a circle or an X. Note here that the mean is slightly to the right of the median, and that's because the right whisker is a bit longer than the left whisker, which means I have some high values here which are pulling the mean to the right. Also note that in this picture, the box and whisker chart is drawn horizontally. We can easily turn it 90 degrees and make it vertical, and it doesn't change anything. The box is still a box, it just looks vertical. In fact, in Excel, when we draw box and whisker charts, we will see them as vertical. So let's draw box and whisker charts for our example data. That's a box and whisker chart for our example 1, and that's for example 2. Notice that I have kept the scale on the y-axis the same, so we can compare them side by side. Now I'm just showing you these values so that we can see a direct correspondence between these values and the chart here. So for example, the lowest value of 125, this 125. The lowest value here is 1350. The highest value here is 1475. The highest value here is 1950. The box, the lower edge of the box is quartile 1. Q1 is 310. So that's at 310. Upper edge of the box is Q3, quartile 3, 725, 725. Here the lower edge is quartile 1 at 1500. That's at 1500. And the upper is at 1720. Median is at 420, which is the same as Q2. So this is at 420. Here the median is at 1640, which is the same as Q2. The mean is shown as an X here at 554. Here the mean is shown at 1618. See here the mean is higher than the median because these higher values are pulling the mean higher. And here the mean is actually lower than the median because there's some low values pulling this lower. Okay, so those are the things we can do in terms of summary measures and charts for ungrouped continuous quantitative data. Next, we will convert the ungrouped data into grouped data so we can do some more things. Converting ungrouped data into grouped data. So that's our example 1 and that's our example 2. Here we have converted this into grouped data. So what did we do? We created what is called a frequency table of bins. So we have created these 7 bins. Now 7 is not a magic number. We could have created 5 bins, 8 bins, 6 bins. Not too many, not too few. 5 to 8 seems like a good number of bins. So what we do is we find the minimum value here, which is 125, and we find the maximum value, which is 1475. We find the range, and if you're interested in say 7 bins, we divide it by 7 and find an approximate bin size. So an approximate bin size came out to be 200. So we go lower than the lowest value and start the bins from there. And we make sure that we have covered the highest value in the last bin. So that's how we create bins. Once we have created these bins, then we figure out how many of these fall in each bin. So see, I have 25 of these. So all 25 have been accounted for. Each value is in one of these 7 bins. Also notice that I have 300 here as well as 300 here. So what if I had an exactly 300 value here? Will it belong to the first bin or the second bin? The answer is it will belong to the second bin. That's just how it goes. So this 5 is saying that 5 of these values are greater than or equal to 100 and less than 300. 9 of these values are greater than or equal to 300 but less than 500, and so on. Now once we have the frequency table, then there are some other things we can do in terms of descriptive analytics. Second example, here the range was not that high, but we still wanted to create 7 bins, so the bin size reduced. So here the bin size is only 100. Once we have created the bins, we can create the frequencies. But we have to make sure that we have accounted for every value. So as long as the sum matches the total number of values here. Now there will be a separate video that shows you how to go from here to here. So once you have the frequency table, we can extend this table to include a cumulative frequency column, a relative frequency column, and a cumulative relative frequency column. So what's cumulative frequency? First frequency is the same. Second one is cumulative, that is 5 plus 9. So previous plus the new. Previous plus new, 18. Previous plus new, 21, and so on. What's relative frequency? This divided by the total. So 5 divided by 25 is 0.2. 9 over 25 is 0.36, and so on. And then we do cumulative relative frequency. So when we do cumulative relative frequency, the last cumulative relative frequency should always be 1.00. So this is the extended frequency table for the first example, and here's the extended frequency table for the second example. Now using this table, we can draw a histogram like this, for example 1, and a histogram like this for example 2. So the heights of these columns is equal to the frequency. So 5, 9, 4, 3, 2, 1, 1. Notice that in this histogram, there is no gap between these two columns. It's all one continuous area. And the reason for that is because there's no break here. See, this is because this is continuous data. Remember, continuous data, there's no break. So we don't want to show any gaps here. So when we don't have these gaps, we call it a histogram. If we have gaps, that would make it discrete. So if this was not continuous variable but discrete variable, then a histogram will not make sense. Instead, column chart would make sense. We will see an example of that a little bit later. Once you have the histogram, you can also create a frequency polygon. So just connect the frequencies 5, 9, 4, 3, 2, 1, 1. So that's the frequency polygon. Similarly here, that's the frequency polygon. Now, if you imagine this line without the histogram, and you can say, well, that looks like a line chart. But I want to caution, note, the frequency polygon may look like a line chart, but it's not. It's a frequency polygon. Line chart is used in the context where the x-axis has time dimension. Here, there is no time dimension on the x-axis. We have bin ranges. Okay? So as an analytics professional, you should be very careful about these minor details. Another chart is ogive that we will see on the next slide. So for the same frequency table, so we have this cumulative relative frequency. So we are plotting these cumulative relative frequencies in this example and cumulative relative frequencies in this example. So this is called an ogive. So this also tells a story. This tells that most of the gain happened initially and then there was not much gain later on, which means most of these values were in the low range, only few values came later. Here on the other hand, the gain is happening quite uniformly till the end. Only towards the very end the gains were less. The gain is happening more uniformly here, and only towards the end the gains were small. So just the shape of this tells a story, which is very hard to tell when we had ungrouped data. So by grouping the data, we are able to tell some story about this data that we could not have if we had not grouped it. Alright, now let's move to discrete quantitative data. So here's an example. Instead of order amount, I have quantity ordered. So 1 unit was ordered, 2 units were ordered, 5 units were ordered. And here's a second example. So this is discrete, and there's not many values. There's few unique values. There's 6 unique values here, maybe 6 unique values here. Now all these summary measures that we learned, we can apply all those summary measures to this as if this was continuous. So all the formulas we used for mean, median, mode, variances, ranges, kurtosis, skewness, we can apply them here as well. But when we convert it to grouped data, there's a slight difference. Here we don't have bins of range of values. We have each unique value. So that's a difference. Similarly here, we don't have a range of values. We have each unique value. And then we can use this to compute the extended frequency table with cumulative frequency, relative frequency, and cumulative relative frequency. And instead of a histogram, we draw a column chart. Similarly, for second example, a column chart. So here we have gaps because there is no continuity between 1 and 2. There is no 1.5. There is no range. So that's the difference between continuous and discrete. If it was continuous data, then a histogram makes sense. If it's discrete, then a histogram does not make sense. Unless there are so many discrete values, like millions of discrete values, that the breaks really don't mean much, practically. Then you can draw a histogram. But you should be careful. As an analytics professional, you should know these nuances about what is more appropriate for what type of data. Instead of a column chart, you could also draw a bar chart, which is nothing but a horizontal column chart. There's really no difference. Sometimes we prefer bar charts if we have lots of these unique values. Bar charts just look a little bit better if you have lots of these values, but qualitatively there is no fundamental difference between the two. Okay, so that completes our lesson on descriptive analytics for univariate quantitative data, and we did it for both continuous and discrete, and both ungrouped as well as grouped.